Hello, this is Mr. Tejada, and I decided I would do this example worksheet, solve this guys for you, and post it to YouTube, and then post it to our classroom website. So if you guys have any questions on how to work through these problems, rather than just looking at the answers, kind of take you through the process, and hopefully that'll help you out. All right, so first of all, it would probably help you if you did read Chapter 8, pages 312 through 325. There's a few equations that are in there. I have a separate sheet of paper that I'm going to use a few times. But here's the other sheet of paper. And this I printed it off from the textbook from page 318, section 8.2 in Chapter 8. And up above what we have is we have the wave equation, and usually this is kind of like the chemistry joke where you say, hey, what's new? Well, your response should be, well, C over lambda. That is pronounced nu. That's the Greek letter for that. And nu stands for the frequency, and this is going to be in hertz, or it will be cycles per second, which is kind of a strange unit to begin with, but it's 1 over seconds. That means kind of like how many waves per second or how many cycles per second. And sometimes you also see it written as seconds to the -1. Over on the right-hand side for the wave equation is up here is c. Now, this is going to be the speed of light, which is the fastest known thing in the universe, 3.00 times 10 to the 8th meters per second. But I think in freshman year when you were doing physical science, I think they didn't use, they used the wave equation, but they had it arranged a little bit different, and some of the variables a little different too as well. Instead of having c right there, they had velocity, which was v, which is kind of close to this one right here. So it can be a little bit confusing, but I'm using the one from the textbook, and hopefully that helps you out, so that it matches up with the readings and with the problems on Mastering Chemistry, or with this worksheet as well. And then this right here, this is going to be the Greek letter lambda, and this is wavelength in meters. So there's the equation. It's a 3-variable equation, not a complicated one. Maybe the most complicated part of it is sometimes you have wavelengths that are not going to be in meters, and you do have to convert those using the metric system from, say, nanometers or anything else into meters, so that it does match up with what's going on up above. That's maybe the trickiest part of it. Down below is one for the energy of a photon, or is also called a quantum of light. And this is, anyways, here's the equation. It's the energy of a photon equals h, which is going to be Planck's constant, times the frequency. So a lot of times you're given, you got to figure out the energy of a photon, or you're trying to figure out the minimum threshold needed to eject an electron using the photoelectric effect. I'm not going to cover that for this lesson, but anyways, sometimes you have to be able to solve this equation up above, so that you can then, for this right here, so that you can plug it into this equation over here down below, so you can figure that out. So it's kind of like a series of equations. You can also rewrite this, by the way, where the energy of a photon equals Planck's constant times c over lambda, which, since frequency equals c over lambda, you can just substitute that in, and there you go. Planck's constant is kind of a funky number there. It's 6.626 times 10 to the -34 joules times seconds. And so when you have this number multiplied by a number that is 1 over seconds, the seconds is going to cancel out. You're going to be left with joules, which is the units that we use for energy in science. All right, so there you go. And let's go back to this. So this is a very straightforward problem right here. Sometimes, if you're not always using the speed of, or the velocity of light, even though this chapter in this lesson is centered around light, it really does help to have a basic understanding of how waves operate and what they are. Anyways, so wave has a frequency of 22 hertz and has a wavelength of 4.0 meters. What is its velocity? So it does help if you have, hey, here's nu over c over lambda, and you can use this equation. The part that we do have is the 22 hertz. So we have 22. I like to change it right into 1/2 just because it ends up canceling itself out just a little bit better. I'm going to switch up pens here because I don't like how that's coming up on the screen. I'm going to use maybe a fine tip Sharpie instead. See if that works a little bit better. Yeah, it does. Okay. Trial and error, right? Nothing wrong with that. 22 over 1/2 equals, and you're really trying to find what C is, and then the wavelength is 4.0 meters. Solve for this, and C is going to equal, well, 88 meters per second. And then finally, box your answer. By the way, it does say write out these problems on a separate sheet of paper. If you can fit these in on this one, that's fine. I don't have a problem with that. The answers are on the back page of this, and this is the second page. And it's down here at the very bottom. So if you can see that, we just did the first one. There it is, 88 meters per second. Should be good to go. All right, what is the frequency of a wave if it's, on to the second one. What is the frequency of a wave if its wavelength is 3.6 times 10 to the negative 9 meters and its velocity is 3.0 times 10 to the 8th meters per second? I always like to do 3.00, but hey, this has 2 sig figs for both of them, so at least you don't have to figure that out. All right, what's the frequency? So now we have this equals C over lambda. I don't know why I always write down the same equation. I wrote it up above, but it just kind of seems to help me out. And then we'll put this up here. So this is 3.0 times 10 to the 8th meters per second. And then down on the bottom is going to be, that was that right there. And then the wavelength is going to be 3.6 times 10 to the negative 9 meters. Now, the most common mistake whenever you're using scientific notation is the fact that, well, when you do this, make sure that you plug it into your calculator and put that into parentheses. If you don't, you're going to be off by a considerable amount. Your raw number will be fine like as far as like before the times 10, but the exponent that would be grossly off if you don't do that. And that's it. I know we've covered that quite a bit in class. I just want to re-emphasize that and make sure that nobody makes that same mistake. So 3.0 times 10 to the 8th divided by, put it in parentheses right there, and do 3.6 times 10 to the negative 9, close it off, and we get 8.3 times 10 to the 16th. Oops, that's not the one I want. Meters are going to cancel out right there, and then you're going to be left with 1/2, or you could write this as Hz, or you could write it as hertz. There's a lot of different ways you can write this. Doesn't really matter which way. And let's double check, see if we're right. Down over here, number 2, 8.3 times 10 to the 16th hertz. There you go, and we're good to go. All right, sweet. All right, as you move across the continuous spectrum from red to violet, what happens to the wavelength? So let's go up to the very top. Here's our red. Here's our violet. You should know this, by the way. There are 7 colors of the rainbow. It's the most magical number in the world, or universe for that matter. So this is going to be Roy G. Biv. There's 7 of them. So red, orange, yellow, green, blue, indigo, and violet. I don't really see much of a difference between indigo and violet personally, and I don't know why we call it violet. We could just call it purple, but whatever. So as we move from left to right, from red to violet, what happens to the wavelength? And you do want to be able to kind of pay attention to what these are right here. So here's the wavelength, and it actually shortens up. It increases as you go from right to left. So if we're going from left to right, it should shorten. And what happens to the frequency? Well, the frequency increases. And these Well, these are inversely proportional to one another. And one way to kind of look at this is that if you're looking at the speed of light and you assume that it is constant, it's not going to change the speed. I know that it can. You can get slowed down, stuff like that. But if you have what's new, c over lambda, if this is your constant right there, and it's going to always be the speed of light, you solve for that. C is going to equal this times that, and that gives you an inverse relationship. So in other words, as one goes up, the other one goes down, and vice versa. And these will always equal 3.0 times 10 to the 8th meters per second. In fact, whenever you're reading this graph right here, it might be a little bit grainy, but if you were to take this value right here and this value right here, the wavelength, and you multiply that by the frequency, this would be actually 3 times 10 to the second. And then if you were, and that is wavelengths, and I guess I should probably put that in there, meters. And then this one down at the bottom is 10 to the 6th, 1 over seconds. And guess what? Everywhere on there, it is always going to equal the speed of light. So if you're talking about this point and that point, speed of light, this point and this point, that's going to be speed of light, so on and so forth. Any place on this, you're always going to get 3.0. If you multiply the top number by the one that's down in the bottom, you're always going to get 3.00 times 10 to the 8th meters per second. Kind of nice. All right, number 4. Beam of microwaves has a frequency of 1.0 times 10 to the 9th hertz. A radar beam has a frequency of 5 times 10 to the 11th. Which type of radiation has the longer wavelength? All right, so let's just go up here and kind of figure out where they're at. So microwaves, where are we at? All right, microwaves right there. And radar beam. Well, it's not on there, but I'm sure we can probably figure out where it is. So this is 10 to the 9th. So down here on the frequency, this is 10 to the 4th, 10 to the 6th, 10 to the 8th, 10 to the 10th. Hey, somewhere halfway in between there, between 10 to the 8th and 10 to the 10th. This is really what we're looking at right there. That's the spot. All right, and then a radar has 5 times 10 to the 11th. So that would put that right here. So there's your radar, which looks like it's operating within the, well, in the almost in the microwave region, so to speak. So which one has the longer wavelength? Well, wavelength increases as you go from right to left. So I'm going to have to say microwaves. Is nearer to the visible light spectrum? Well, that's the radar. That's just because it's right here, and that one's over there, and this one's over there. So it's closer to X-rays. Oh, X-rays is over there too, so it's radar. All right, done with that. All right, this is actually a pretty good problem. This is one of the tougher ones on here. Number 5, a bright line spectrum contains a line with a wavelength of 518 nanometers. Determine the wavelength in meters. So this is one of those examples that I was talking about at the very beginning, where if you have the wavelength in nanometers, you got to first convert that over into meters. So that's what we're going to do right there. So we have 518 nanometers. Which coming from? Which going to? Nanometers down on the bottom. Meters is up on top. 10 to the 9th is down there on the bottom. And you get 1 meter up on top. And if you plug this into your calculator, which I will do for you. .18 times 10 to the negative 7th. Nanometers cancel out. Left for what you want. And we're done. Cool. Frequency. What's new? Not much. Just staying at home. C over lambda. Sorry if that's funny only to me. Over wavelength. So 5.18 times 10 to the negative 7th. My 8s really kind of suck today. And that's going to be meters. Meters are going to cancel out right there. Make sure you put that into parentheses. And let's see. I'm going to go 3.00. Let's clear. Times 10 to the 8th divided by, got the parentheses, 5.18 times 10 to the negative 7th. Close it off. We get 5.79 times 10 to the 14th. And that's going to be, well, hertz. Hertz just sounds fancier. Makes you sound smarter. Or at least it does for me. Let's double check that one. Let's go to the back. No, I mean the other sheet of paper. Number 5. 5.79 times 10 to the 14th. Let's see. 5.79 times 10 to the 14th. Sweet. All right. Now what we're going to do is we're going to use that amount and we're going to plug it back into this equation right here using the energy of a photon equation, or quantum of light, which is like a packet of light. I think the saying that I used in class was, is just as a atom is to matter, a photon is to light. So it's the smallest amount, smallest packet amount. So E equals H times nu. This is going to be equal to 6.626 times 10 to the negative 34 joules times seconds times 5.79 times 10 to the 14th, 1 over seconds. Converted that over into 1 over seconds, so the seconds can cancel out. And let's see what we get. .84. Rounded. Sig figs. What do we got? Hey, we started off with 3. We're going to keep it at 3. 3.84 times 10 to the negative 19th. Capital J for joules. All right, good to go. What's the color of the line? And this is page 145. I'm going to cross that out right now because I know it's on page, with our new textbook, page 318. So, here we go, 318. This is the one that I printed out from there. You can go to the eText and click on this, blow it up like this and kind of see where it's at. Now, there are 2 ways to do it. You could either do the frequency or you could do the wavelength. And it really doesn't matter which one you use because it's going to give you the same answer. But if I do 5.18 times 10 to the negative 7th, over here, 5.18 times 10 to the negative 7th, or we could just go to the very beginning of this. Where's it at? 518 nanometers. That'd be easier. That's what I'm at. So 518 puts us about right here. And what color would you guys say that is? If it is, I guess I should have gone like, hey, if this is 550, this is 525. I'm kind of guesstimating best I can. I'm going to say that's green. And let's see if I got the same answer from before on the back page. Looks like I didn't put it in there. Shame on me. I guess we went 5C and didn't do 5D, but because we can, 5D is green. Cool. All right, so we're done with the first page. Halfway there. All right, let's go on the second. A photon has an energy of 4.00 times 10 to the 19 joules. Find the frequency of the radiation. So now we're just going to basically go from going forward, going in reverse. So if we have E equals H times nu, and this is going to be 4.00 times 10 to the negative 19th joules. This is going to be equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. And then solve for frequency. So divide this by the 6.66 times 10 to the negative 34 and you'll get your answer. Let's do that. So let's go 4.00 times 10 to the negative 19 divided by, start the parentheses, 6.626 times 10 to the negative 34, close the parentheses, and we get 6.04 times 10 to the 14th. Let's double check our work. 6a, 6.03 it says right there. Well, I guess 6.04 would be a little bit better, so let's just use that. Close enough though. All right, wavelength. Now we want to use, hey, well, what's new? Well, C over lambda. All right, use that equation. Shoot. This is one thing that students oftentimes find difficulty is how do you solve for this guy down at the very bottom? Well, let's just get him out of the bottom right there. So if I multiply both sides by lambda, now you got lambda over here. So, and then if you divide this by the new, and then this had canceled out, so now it's divided by the new. And so what you have is a rearrangement of that equation to where you have the wavelength is equal to speed of light over new. So I guess that's the new equation. Ha 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 ha. No pun intended. Actually, pun was totally intended. All right, so this equals 3.00 times 10 to the 8th meters per second divided by frequency. Frequency we just figured out to be 6.04 times 10 to the 14th. 1 over seconds. Switched it over again. Seconds is going to cancel out. You're going to be left with meters, which is what you should have. And I'm going to go 3.00. I don't know why that my calculator's all screwed up. 3.00 times 10 to the 8th divided by parentheses 6.04 times 10 to the 14th. Boom. And we get 4.97. So what I got down here? Yeah, I did. Cool. All right. 4.97 times 10 to the negative 7th meters. Cool. All right, the region of the electromagnetic spectrum that this radiation represents. So pick your poison. Which one do you want to use? Doesn't matter. You could either use this one right here, this guy, or you could use something like this. I'm going to use the one that you guys already have. So there you go. All right, let's use wavelength because that's the last one we did. 4.97 is pretty close to 5. So I'm going to say that's close to 5 times 10 to the negative 7th. So 5 times 10 to the negative 7th. Puts us in about in that region, I would say. What did I say down below? Didn't say anything. Well, let's try the top one, see if it matches up. You have 6 times 10 to the 14th. All right, 10. I think I did do it wrong. I went the wrong way. Haha. All right, this is me just thinking. I don't want to mess something up here. All right, 6 times 10 to the 14th, 10 to the 12th, 10 to the 14th. I got them in different regions. I don't know why I did that. That doesn't make any sense whatsoever. Let me come back to this one. No, let's do it right now. There's 4. There's 6. There's 8. Halfway between 6 and 8. Okay. I just looked at it the wrong line. So if that's there, halfway in between. So you're looking at about right there for both of them. And since this is 10 to the 12th here, 10 to the 14th is 10 to the 16th. So that seems about right. So I would say that this is infrared. And I should probably put that in at some point. Onto the revised version. Too late for it this time, though. All right, same thing as above. A photon of light has a wavelength of this. Find the frequency of the radiation. So a photon of light has, all right, what's new? See it over lambda. 3.00 times 10 to the 8th meters per second. Wavelength goes on the bottom, 3.20 times 10 to the 5th meters, put it in parentheses, and then I'll give you that. I got 937.5. Seems like an odd number, don't you think? 7A. Yep. 938. That's what I got last time. Alright, so we're good there. Energy of a photon. Planck's constant, so 6.626. And 6.21. Number 7C. Hmm. 7B, I mean. 6.21 times 10 to the negative 31. Cool. And that would be joules. All right, region of the electromagnetic spectrum this radiation represents. See if I can not mess this one up. So 938 hertz. Let's see where that is. 938 hertz. Well, 3 times 10 to the second that's about 300. Yeah, that's not what I want to do. Hertz is going to be on the bottom. So maybe use the other one. 3 times 10 to the 5th. Let's do that. 3 times 10 to the 4th to the 5th. We're talking about way the heck over here. So I would say that that is radio. All right, determine the frequency of light that has this. I don't know why there's so much more room there, but whatever. What's new? C over lambda. Okay. Oh, gotta do a quick conversion right there. That's in centimeters. 100 centimeters in 1 meter. So this should be 4.257 times 10 to the negative 9 meters. All right. All right, let's see what we get. Ooh, notice what I did there? I did not put that into parentheses. I'm going to start over. $7.05. Nope, that's 4 sig figs. 7.047 times 10 to the 16th. So I got the same number again. Good. Getting there. Getting there. All right, this one I think is actually pretty darn long. So let's try this one. How many minutes would it take a radio wave with a frequency of 7.25 times 10 to the 5th hertz to travel from Mars to Earth if the distance between the two planets is approximately 8.0 times 10 to the 7th kilometers. All right, how many minutes would it take a radio wave? See, I've not done this one for a while, so I want to make sure that I do this correctly. All right, how many minutes would it take a radio wave with a frequency this to travel from Mars to Earth? That is a trick freaking question, because it does not matter, because all things that are light are going to be 3.00 times 10 to the 8th meters per second. That's its speed. So we want to know how long it takes to get there, so we're going to know what the speed is. All right, Mars to Earth, the distance is 8.0 times 10 to the 7th kilometers. Got to turn that into meters first. So for every 1 kilometer, you get 1,000 meters. So that's going to be 8.0 times 10 to the 10th meters. All right, cool. So if you go 8.0 times 10 to the 10th meters, which come from, which going to, you can use this as a conversion. 3.00 times 10 to the 8th meters per 1 second. All right, we want to know how many minutes. So there are 60 seconds in 1 minute. That should do it. I get 4.44. Hey, look at that. 2 sig figs, 4.4 minutes. All right, not a bad one. All right, cobalt-60 is an artificial radioisotope that is produced in a nuclear reactor for use as a gamma ray source in the treatment of certain types of cancer. If the wavelength of the gamma radiation from cobalt-60 source is 1.00 times 10 to the negative third nanometers, calculate the energy of a photon of this radiation. All right, so we know that we got to turn that into meters. So we got 1.00 times 10 to the negative third nanometers. Did that a little funky. And I believe at the very beginning page we had the conversion from meters to nanometers. All right, 10 to the 9th, there it is. 10 to the 9th nanometers to 1 meter. So 10 to the 9th nanometers to 1 meter. So this should be 1.00 times 10 to the, since it's on the bottom, that's going to be subtracting. So negative 3 minus 9 is going to be negative 12 meters. That is its wavelength. All right. If the wavelength, now we have that into that, so we need to figure out the frequency and then take the frequency and turn it into it. Or we could use, from the very beginning problem, where we have this equation right there. That's what I'm going to use instead. Cut down on the step. E equals h times c over the wavelength. This is going to be 6.6226 times 10 to the negative 34 joules times seconds. And then up on top is going to be 3.00 times 10 to the 8th meters per second. And then on the bottom, we're going to use the 1.00 times 10 to the negative 12 meters. And let's see what we get. And hey, look at that. It's the same as the one down below. It's the same as that guy. So 1.99 times 10 to the negative 13. And I wrote out joules all the way there. There you go. All right, so this was